the first question is that what is computer science?
Okay, computer science is the study of computation. What does it mean for a sequence of changes to make it compute things? The most interesting thing is that computation happened a lot earlier than when computers were invented. In other words, computers were invented in the 1940s, but people were dealing with processes of calculating things or finding out things long before that, for hundreds of years before that. And we'll see some of that later on. We'll see some problems that the ancient Greeks dealt with and how you calculate certain things. So how do processes work on, and how do we calculate things, and what's calculatable and what's not calculatable and stuff like that. That's what computer sciences deal with. But also nowadays there's a lot more to it. Nowadays is how do you build a better computer, and how do you build a more efficient computer, and how do you build a quantum computer? All these things are what computer scientists study and work on.
Sir, you use the word quantum computer. Sir, what is quantum computing? That was also one of the questions.
A computer works with electricity, and you have gates, which electricity flows through the circuits, or does not flow through the circuits. About 20 or 30 years ago, they started thinking about making computers that use quantum physics in it. Okay, and quantum physics has some very strange properties, like a particle can be in, we spoke about this yesterday, a particle can be in more than one position at one time. So what quantum computing is all about is trying to use this quantum physics, or the strange properties of quantum physics, to get computers to be better. So let me give you an example. If you wanted to search for something in a file, here's what you do. You look at this position, you look at that position, you look at that position in the file, you keep on going through all the positions, okay? Well, that would take a long time because you have to go through all the positions. But how about if we can use a quantum computer, and put somehow in a superposition, we talked about that last time, not a position, not that the particles are not in one place at one time, but they're in many places at one time. And what you do is you try, instead of looking at this position, this position, this position, this position, you go into a superposition and you're looking to many positions at one time. So it is believed that quantum computers will be a lot quicker than classical computers, okay, if we can learn how to make them properly. Okay, and so this is a field that's very much in the news today, of people trying to build computers which are based on quantum physics and which work much better and much quicker. Yours humbly, I wrote a book on it called Quantum Computers for Computer Scientists, me and someone else, and it's a very readable, understandable book on quantum computers.
Sir, in near future, what can be some of the breakthrough applications in quantum computing?
Okay, so one of the things that computers are good at is cryptography. Cryptography means you hide your data. So, for example, if you wanted to buy something over the internet, you enter in your credit card information or your private information, and only that company can read that information, and they can take your money. A classical computer can do that with ease. Hold on a second. So the way it's done is called something called RSA. RSA is some type of protocol that makes you saves money. I'm sorry, can we press pause for a second? This is very important. Okay, I'm sorry.
No problem.
No.
Okay, so you want to start again?
Yes, sir. Sir, you mentioned the RSA encryption.
Right. So quantum computers will, so RSA is a way of computers communicating with each other without revealing information to anybody else. Okay, it's based on something called factoring, which we'll talk about more in chapter 5. But the point is that when a quantum computer is built, RSA will be destroyed. In other words, if you have a quantum computer now, you will be able to read other people's information and find out other people's information. So what can we expect? We can expect that RSA will be destroyed when we have a quantum computer. There's other things also that people talk about. There's a lot of hype Hype means people are excited about it, but it's not necessarily true about quantum computers, but it is a fascinating field worthy of study.
So you mentioned the RSA encryption and the prime factorization. Peter showed that quantum computers can do some things that classical computers would not be able to do. Can you explain that thing also?
Okay, so let's talk about factoring. Okay, you ready? Take two numbers. It's very simple to multiply them and get out a larger number. Now let's say I ask you, here's a large number. It's made out of two numbers. Okay, in other words, it's the product of two numbers. Okay, question. Find those two numbers. Okay, that's called factoring. In other words, if I give you the number 15, you can say to me, oh, that's 3 times 5. If I give you the number 100, you'll say, oh, that's 5 times 20. Okay, that's factoring. Now, RSA is based on the following thing. I'll give you a number. The number is 300 digits long. Okay, now find, and it's only got two factors. You can only divide it by two, with two numbers go into it. Tell me what those two numbers are. And the answer is that's a very hard problem. Okay, that takes a very long time for a classical computer to do, especially when you're dealing with something like 300 digits. Okay, however, a quantum computer can do that with ease. Okay, a quantum computer can factor numbers with ease. Okay, now RSA is based on the fact that factoring numbers is very hard. And so if you have a computer that can factor numbers with ease, in other words, in a short amount of time, then RSA will not work anymore. Now, don't get nervous, because the computer scientists are already working on other different types of things, which quantum computers cannot do, and which you can encode information and hide information. So yes, quantum computers will destroy RSA, but they won't destroy cryptography. There will always be another method in which you can hide information and do things like that.
So do you think there is a hype around quantum computing to much more than what it would really be able to accomplish?
In other words, is there some type of computer that's even faster? So you're gonna have classical computers, then quantum computers, and then something even more. There's always technology constantly improves. Technology constantly is the only thing that changes. Hopefully there will be something. I'm sure there will be. In some sense, I think a human being is more advanced than a quantum computer. Okay? Human beings can do things that quantum computers can't do. We have a sense of morals. We have a sense of aesthetics. We can tell when a picture is beautiful. We can fall in love, et cetera, et cetera. So there's a lot of things that we can do that quantum computers can't do. But I'm sure there's going to be some technology 30 years in the future that's going to say, oh, you know, quantum computers, they're old-fashioned. These are the new hot things.
Sir, one question regarding this quantum computing. So we know we are getting the benefits of quantum computing, but what are the challenges which is presently being faced in the quantum computing?
Okay. Okay. So this thing that quantum is can be in more than one place in one time. Okay, which is something we spoke about before. That's a very strange thing. You don't see that. Okay, in this world, you see, you know, this object is here, and this object is here, and this object is here. It's always in one place. Okay, and the reason is because when we observe things, they're always in one place. Okay, when things are part of the larger world, they're in one place. But quantum things, subatomic particles, can be in more than one place when they're not interacting with the world. So one of the hardships of making a quantum computer is isolating it from the rest of the world so that it can be in more than one place at one time. Okay, if you can isolate something, it will do that strange quantum type of stuff. The hard part is, how do you isolate things? Okay, so the engineers are having a very hard time coming up with quantum computers because they find it very hard to isolate things. Okay, so quantum computers are usually in a frozen environment. It's very close to, you know, absolute zero, so nothing else will interact with it. It's very that's the hardships of making it. But again, eventually they will be able to do it. Another hardship is that quantum computers, the quantum physics is based on a lot of probability. In other words, as opposed to that, classical computer, if I throw this, I can tell exactly when it's going to fall and where it's going to land, et cetera, et cetera. Quantum computers, you have a lot of probabilities working there, and you don't want your computers to work with probabilities. You want your computers to be somewhat exact. So that's why quantum computers are a little bit hard to deal with, because we're used to computers that give exact answers, not probabilistic answers. I can elaborate if you want.
Yes, sir. Please elaborate, sir.
Yes, sir, please.
Okay,
please.
okay. So classical computers are what's called deterministic. In other words, at every point, you tell the computer, oh, if this is here, then do that. If this is here, then do that. That's what programming is all about. Telling the computer, I want to add up all these numbers. I want to give the exact answer to this and that. So they work with, classical computers work with data and manipulate data in a set fixed way that you can tell exactly how it works. Okay, as opposed to that, quantum physics is very random. So if I give you a subatomic particle that's working with quantum physics, and I say, what's the energy of this particle, or where's the position of this particle, it won't give you exact answers. When you measure things, you don't get exact answers. What you say is, there's a 20% chance that the energy is 58, and there's a 30% chance that the energy is this, and there's a 1% chance that the energy is this. So you're not getting exact answers for things. And when you try to build computers based on that type of physics, you get in trouble, because you want your computers to give exact answers. You don't want that the computer should add three numbers and say, oh, there's a 10% chance that the sum of these three numbers is this. There's a 20% chance that the sum of these three numbers is this, and there's a 3% chance that the sum of the three numbers is this. You want exact answers. So for that reason, it's hard to come up with quantum computers, because quantum physics is based on a lot of probability, but we're used to having our physics based on our computers to give exact answers, not to be probability answers.
Is funding one of the factors in slow progress on quantum computing?
Sir, is lack of funding for research one of the process
lack
for
of funding? No. I mean, many people would say that, and they'd say, oh, the government should help support quantum computing. But no, there's some deep theoretical issues going on there, and both of the issues that I mentioned are very hard to do it. Now, when you throw money at a problem, it could help to solve it, but in this case, there's a lot of theoretical problems. In other words, they just don't know how to do it. In the last chapter of this book, I show how you build a quantum computer, and I show that there's a lot of different schools of thought of how to do it. Okay, the engineers simply do not know how to do it. That was the hardest chapter to write, because there wasn't an exact way of doing it. And every single school and every single startup that's doing quantum computing, they're having a very hard time knowing how to do it. So, of course, giving more money would help put more people working on it, but there's still a lack of information. As opposed to that, classical computers, all my computers and your computers, they're all made the same way. We all know how to deal with circuits and transistors and whatever, and they're pretty much very, very similar. So we know how to do classical computers. We don't know how to do quantum computers, and just more money is not going to help us. We need more intelligence in some sense.
So one question is, you said that isn't it a corollary question to this is, we know exactly the algorithm, we know the steps that a classical computer takes to carry out a computation. With a quantum computer, we lose that power. We don't know exactly how the quantum computer is carrying out its computation, right?
No, we know how the quantum computer is getting out. We know what the quantum computer is doing, and we're telling it what to do. The problem is the results of doing it are problematic. So, for example, in a classical computer, you would have a programming line saying, if the user presses in these three letters, that means you should play again. So, for example, at the end of a computer game, the computer says, would you like to play again? Yes or no. So if the user enters Y, then you play again. If the user enters no, you don't play again. Okay, that's very good. With a quantum computer, it won't be able to read the information exactly. You know, you would have something like, if this particle is here, then do this, or if this electrical circuit is on, then do that. Well, the problem is that quantum particles don't have exact values. They're a little bit here and a little bit there. That's what we talked about, superposition. And so it's very hard to interact with that because of that probabilistic, not exact type of things that they're dealing with. Okay, the particles that they're dealing with are in a superposition. They're not in a position.
So what is the relation between artificial intelligence and quantum computing?
Artificial intelligence is a branch of computer science, how to make computers more intelligent. Okay, and it's a very complicated thing of how you measure how intelligent a computer is. Okay, and quantum computer is another branch of computer science trying to get people to trying to get computers to work with quantum mechanics. Now, there are some people who say, "Oh, listen, if we only got computers if we had quantum computers, we'd be able to work better with artificial intelligence." Okay, maybe those are quicker or not. I don't think anybody has any good results in that area. Anybody saying that, oh, you know, we did this project with artificial intelligence and we used a quantum computer, therefore quantum computers are perfect for artificial intelligence. Okay, it's not so simple like that. People are excited about quantum computers and they want to apply quantum computers to artificial intelligence. But as far as I know, there's no results. However, there are those who say, oh, look, we want computers to act like human beings. Human beings' brains work with quantum ideas. It's not clear that that's really true, that human beings work with, you know, subatomic particles, whatever. And some people say, well, if you want a computer to act more like a human being, then let's use a quantum computer because it's more like a human being, a quantum effects. I don't know that that's really true, and I don't know any results that actually show that. Okay, the human brain works with neurons and electricity passing through neurons and what's called synapses and stuff like that. I'm sure there are some quantum effects, but I don't know how it works, and I don't think anybody else knows either. Consciousness is a very hard thing to deal with. But just one more other thing. It's very hard to say what artificial intelligence is because in some sense we have computers doing intelligent things already. Look at this computer that we're all talking on. Okay, we're communicating. It's recording. We're doing. We're dealing with each other, et cetera, et cetera. It seems like a very intelligent thing that the computer's doing. So it's hard to define what artificial intelligence is. Okay, a soda machine where you put money in and you get out a soda doesn't feel like it's intelligent. But you know, a computer, a word processor that changes your spelling when you spell a word and it changes the spelling, seems to know how to spell words or seems to know what I was intending to spell. That seems extremely intelligent to me. So, in some sense, we have artificial intelligence already.
So one more question.
Please.
Somebody, sir, who is currently studying in high school and he is interested in computer science field. So how he should approach it?
He should get a computer science programming book and program all the exercises in the back of every chapter. That's the only way to really get started. In other words, there's a lot of interesting popular books, et cetera, but the main part of computer science is programming. And if you want to learn how a computation happens or how processes happen, you have to code. You have to really get a feel for it and code. It's like if you wanted to be a math major, you really have to know how to, before you get into the high level abstract stuff, you really have to know how to calculate and do calculus and integrate and differentiate and all that stuff. You really have to get, especially at a young age, you have to get a lot of practice in it. I remember when I was in the first year, when I was 13, 14, 15, I was very much into programming and understanding how a program works and doing things, with loops and stuff like that. So any beginner's programming book, it teaches you how to program a computer. And the trick is not to read it, because reading it is not hard, but to do all the exercises, to really program every single possible thing.
Sir, so can you describe, sir, what will be the future of computer science and information science in a few words?
I have no idea. I've been I was born in the 60s, but I've been when I was 13 or 14, my parents bought me like a baby computer. And the computer I own now is 40 years later, and it's such a different thing. And computers have changed so many aspects of our lives that it's hard to predict. I just, sometimes at night I watch old movies, and you think about old movies like movies from the 40s, 50s, 60s, 70s, 80s. And they didn't have cell phones in those times. And so all the plots, if you think about it, all the plots of the movies are based on the fact that there's no cell phones. Nowadays, if I wanted, I can call you right now from across the world with pressing 15 buttons. I can get anywhere across the world. We can discuss things, et cetera, et cetera. Think about how plots of movies would change. Old movies would change if we had that. So computers have revolutionized our life. Not only computers, but cars and IDs, and you walk down the street and there are cameras taking pictures of you. There's so many things. This week I was in the hospital, and it's just amazing how computers have revolutionized health. In other words, you can use computers to detect this and do this, and it's mind-boggling. So I can look from the past 20 years and say, wow, what a difference from 20 years ago till now. And there's no way I can predict what's going to happen 20 years in the future. It's just impossible to predict. Communication's going to get better. I just can't predict it. Nor can anyone else.
And so this will be like, what are some of the challenges which we expect, which we are facing right now in the field of computer science overall, not like quantum computing, artificial intelligence, but overall in the field of computer science, what are the basic challenges we are facing presently, or which we are expected to face in near future?
I don't know. I mean, classical computers, all computers are making tremendous progresses in every area. But we're going to see in chapter 6, 5, and chapter 5 and chapter 6, there are certain simple problems that I can explain with ease that no computer in the world can help solve those problems. I could talk about them now, but if you want, we can wait till chapter 5 or 6. So there are certain problems that will take trillions of centuries to solve, something called the traveling salesman problem. But these are simple problems. It would take trillions of centuries for any computer, including quantum computers, to solve. So they're not solvable. And then in chapter 6, we're going to see there are certain problems that won't take trillions of centuries. A computer can't do them, period. No matter how sophisticated and how complicated the computer are, we can prove that a computer cannot do them. And so those are interesting challenges. But right now, it doesn't seem like anything's in the way of making progress, and we're constantly progressing. People find, not me, but there are certain people who find, like if you have a cell phone that's 3 years old, it doesn't have good, it's not up to date, so it's not good. You got to trade it in or something like that. I mean, to me, it's a little bit silly, but there are people who have that. But what that's showing us is that even 3 or 4 years, as time progresses, there are amazing changes to simple things like a cell phone.